So let's take a few moments to discuss the stereochemistry of an E1 reaction. So as we view this particular PowerPoint slide, we see that we are subjecting an elimination substrate, an alkyl halide, with a weak base that is a hallmark of an E1 elimination. Notice both the cis and trans alkenes are formed. The trans is the major product because it's a lower energy alkene. The two R groups, and this is extreme because they're both big bulky phenyl groups, are oriented opposite. There's less steric bulk relative to the Z alkene, in which there's significant steric bulk. In an E1 elimination, you will realize both of these products. Now, in an E1 elimination, in an E2 elimination, only one will be realized. So let's take a look at the stereospecifity of an E2 elimination and then compare it to the lack of stereospecifity of an E1 elimination. So I'm just going to redraw our substrate. And rather than drawing the big bulky phenyl rings, I'm just going to abbreviate those functional groups as pH. That's pretty common in organic chemistry. Of course, we also have a methyl group. And we also have a hydrogen. In the E2 elimination, we have a concerted reaction. So we have an alpha carbon, and the alpha carbon is always the carbon that is bonded to our leaving group, our halide. One carbon removed from that carbon is a beta carbon. Any hydrogen that's attached to a beta carbon is a beta hydrogen. A biologist or biochemist would refer to this E2 elimination as a beta elimination. So in a biochemistry context, this is called beta elimination. There is not a single case of E1 elimination in a biological system. E2 is the default elimination mechanism in nature, just like SN2 is the default substitution mechanism that is found in nature. There is a strict geometric requirement for E2 elimination or beta elimination. That is, the hydrogen, the beta carbon, the alpha carbon, and the leaving group, in this case the bromine, must be in the same plane. We call that periplanar. And the hydrogen that I'm going to remove from proton transfer and the leaving group must be anti-relative to one another. Now there is a difference between anti-periplanar and anti-coplanar. Anti-coplanar means that we must have a strict 180-degree dihedral angle between the H and the Br. Experimental evidence suggests that this strict requirement isn't necessary, but it must be very close to 180. So typically, a dihedral angle of 175 to 179.9 is sufficient. So in the E2 elimination, I will have a sufficiently strong base, and we will have a proton transfer. We will form the pi bond, and the bromide is going to leave. Only one of these two possible geometric isomers, and I'm talking about the E alkene and the Z alkene, will be formed with an E2 elimination. In this case, we're going to have the trans. And from a practical standpoint, the methyl group is coming out, the phenyl group is coming out, therefore the methyl and the phenyl have to be on the same side of the pi bond. The phenyl group is going in, the hydrogen is going in, the phenyl and the hydrogen must be on the same side of the pi bond. This is an E alkene. So now let's discuss why we get a mixture of products in the E1 mechanism. So remember, in the E1 mechanism, this is a stepwise mechanism, meaning that we're going to have loss of a leaving group or heterolysis of the carbon-bromine bond, which of course is going to generate a carbocation. I can have rotation about this carbon-carbon single bond such that the carbocation is cis-like, or if I don't have rotation, it is trans-like. Of course, the second portion of this mechanism is going to be a proton transfer, where a base removes the hydrogen atom and you have heterolysis between the carbon-hydrogen bond to form a pi bond, which alleviates the carbocation intermediate. Transalkene or E-alkene versus cis-alkene or Z-alkene. Now let's take a look at a second reaction that's emphasized in Chapter 8 of the Carty text. And this is going to be a substitution reaction. We are going to react phenyl methanol with methyl iodide and KOH, which accounts for the basic conditions. And we're going to convert an alcohol to an ether. So this really, if you want to classify this as a reaction, is a Williamson ether synthesis. And I feel compelled to tell you that ether, you get that or you don't. That is funny, y'all. Don't try to hold it in. So in terms of the mechanism, let's start with our organic substrate, phenylmethanol. Of course, I've discussed this previously. When we draw a terse structure, we really should draw the hydrogen heteroatom bond because it's going to be broken in this process. KOH is really a source of hydroxide with a potassium counterion. So we're not going to worry about the role of potassium. It just is going to associate to form a salt bridge. So the first step of this mechanism is a proton transfer. And the purpose of the proton transfer is to increase the nucleophilicity of the alcohol to an alkoxide. So again, proton transfer. And now this will be phenyl methoxide, which is a much more reactive nucleophile. And I'm going to react this with methyl iodide. This will react via an SN2 concerted nucleophilic attack and loss of a leaving group, or heterolysis, whichever term you prefer. So if you are a Cardi disciple, this is an SN2. If you are a Doc Oz disciple, this is a concerted nucleophilic attack, loss of leaving group. As I've discussed in class, the labels don't matter nearly as much as the process. So whether you decide to call it SN2 or nucleophilic attack, loss of leaving group, concerted, the arrow pushing is the same, and the ether is the product. So I'm just going to abbreviate pH for the phenyl ring. And then we have a CH2, an oxygen, and a CH3. Potassium iodide is our inorganic product that we are not concerned with, but it is going to be present in solution, and it's very soluble, so it will be solvated in whatever hydrophilic solvent that we have.